video, we're going to review some ways to calculate the elasticity of demand. Remember, elasticity is a measure of responsiveness. In this case, we're going to focus on the price elasticity of demand. The basic formula is here. Elasticity of demand, or the elasticity coefficient, is equal to the percent change in quantity demanded divided by the percent change in price. Now, we could calculate elasticity coefficients with respect to other determinants of demand. The income elasticity of demand, for example, is looking at the percent change in quantity as a result of a percent change in income. Or the cross-price elasticity of demand is looking at the percentage change in quantity consumed of one good in response to the change in the price of a related good, a substitute or complement. We're going to focus on the simplest case here and stick with the price elasticity of demand. How much does quantity respond given a specified change in the good's own price? Now, the most straightforward way to calculate this is when we're presented with information that already tells us the percentage changes in quantity and price. For example, here, in example 1, if the quantity demanded falls by 10% after the price rises by 40%, we have all the information we need, we just need to substitute into the correct parts of the formula. So let's rewrite the formula. Elasticity of demand is percent delta QD divided by percent delta P. And let's just substitute. In this case, quantity is changing by 10% and price is changing by 40%. Now, because this is a demand elasticity, we know that a demand curve slopes downward. So technically, my change in quantity is a negative change, while my change in price is a positive change. I'm going to follow the convention of taking the absolute value, but don't forget, prices and quantities move in different directions when we're talking about demand. So I can just simplify my fraction here, and my elasticity coefficient is either 1/4, or if you prefer to do it in decimal form, 0.25. Those communicate the same information. And if I'm concerned about classifying this good or service as relatively elastic or relatively inelastic, because the absolute value is less than 1, what I know here, and I'll just say this, ED is less than 1, that implies a relatively inelastic demand. This is just telling me that quantity responds in a lower magnitude compared to the change in price. We see that price rises by 4 times as much in terms of percent as the quantity adjusts. Now let's take a second example, example 2, just to get familiar with calculating based on this formula. So same thing, we've been given our percentages. All we need to do is rewrite the formula and substitute the correct values in the correct spot in the formula. So my elasticity formula is percent change in quantity demanded divided by percent change in price. What I see here is the quantity rises by 50% after the price falls by 10%. Again, this is consistent with the law of demand. Price decreases, quantity increases. So I'm going to drop the negative sign, but just keep that in the back of your mind. So here I'm going to replace the numerator with 50, the denominator with 10, and that gives me a value of 5. Now, because this elasticity value is greater than 1, that tells me that the elasticity of demand for this product, or for this price range, is relatively elastic. And we can see that here in the ratio. Quantity responds in a more dramatic way relative to the change in price. In fact, quantity rises 50% in response to a 10% price cut. That's a pretty responsive quantity. So we would expect to describe that as more elastic or more sensitive to price. Now finally, if we're given this type of, let me back up and say, sometimes we might see other information presented, but in a way that we can still make use of this formula. So you might be given an elasticity coefficient. So perhaps the elasticity is 0.6. Now I can tell that the price elasticity of demand is inelastic because the value is less than 1. But what if I want to be a little bit more precise? In particular, if I know that the quantity demanded fell by 30%, what was the change in price? Well, again, I can use the formula and just substitute for what I know and solve for the variable that I don't. So my elasticity of demand is percent delta Q divided by percent delta P. In this case, I know that 0.6 equals 30% divided by percent change in price. Now this mathematically is a little trickier to solve, but not impossible. I'm going to come over to this side of the board to give myself a little more room. So what I'm going to do is say my percent change in Q, 30, equals 0.6 times the percent change in price. So I'm taking advantage of cross-multiplying. You can think of putting this over 1 and saying these two ratios are equal to each other. Now, if I divide each side by 0.6, what I will see is my percent change in price is actually equal to 50%. So the change in price, remember, quantity fell by 30%. That tells me, following the law of demand, price must have risen. In fact, price rose quite dramatically by 50%. If we want to actually confirm our math, what we could do is, I'll just draw an arrow here and say confirm or check. If the percent change in quantity divided by the percent change in price equals a 30% fall in quantity divided by a 50% rise in price. In fact, that is equivalent to 0.6. So this is one formula that we can use. Now we don't always have information presented to us in nice percentages. So what we'll look at next is when we have two specific points along a demand curve, how we might go about calculating the elasticity of demand. Now sometimes when we're calculating elasticity, we might not have those nice percentages given to us. What we might see is a specific demand curve. So here's a demand curve that we've seen before. I've written the equation in this format. Quantity demanded equals 30 minus 5 times the price, or Q equals 30 minus 5P. Notice the term on my slope term has a negative coefficient. That just tells me prices and quantities move in opposite directions. We see that from the graph as well. And that confirms that this is, in fact, a demand curve. Now, one thing I want you to remember is that slope is not the same as elasticity. Slope and elasticity are somewhat connected, but for a demand curve like this, the slope is constant. It's always, in this case, if we're doing delta Q over delta P minus 5, if we did it as delta P over delta Q, it'd be minus 1/5. However, the elasticity is going to change along this demand curve. And we'll get to that in a few minutes. First, what I want to show you is sometimes when we have a demand curve, we might be trying to calculate elasticity as the price changes from one value to another. Now, if you've done the reading, you'll see that the problem we run into is depending on which price-quantity combination we pick as our starting point, we can get a different value for the elasticity coefficient. So one way to get around that is to use what's called the midpoint formula, or sometimes this is referred to as the arc elasticity. So I've rewritten that formula here. And as you can see, we've got Q2, Q1, P2, P1. There's a lot of different variables going on here. I personally have a hard time keeping all those straight. So what I'm going to do is try and summarize this in a more condensed form, taking advantage of some old-fashioned math about using fractions, which might provide a little trip down memory lane, but I hope will make this presentation a little bit easier in terms of calculating elasticity when we have a demand curve like this. So the first thing I want you to notice is Q2 minus Q1 is just the change in quantity. P2 minus P1 is the change in price. We're looking at what happens as we move from one price-quantity combination to another, or from one point on the demand curve to another. That's in the numerator of each expression. In the denominator of each expression, we're calculating the average quantity. We sum up the two values, or the average price. We sum up the two prices, divide them by 2. That's giving us the midpoint, hence the name midpoint formula. Now what I'm going to do is rewrite this formula and say what I've really got going on is change in quantity divided by, and I'm going to put this in quotes, some reference or anchor value of Q. It could be the midpoint, or it could be a specific quantity. And I'm going to divide that by rewriting this expression. In the numerator, the change in price, the difference between P2 and P1, divided by, again, some reference value or anchor value of P. Okay, so let me drop those quotes and let's just say we're thinking about a very specific value of elasticity at one point on this demand curve. In fact, I'm going to, because we're talking about the midpoint formula, go to the midpoint of this demand curve. The midpoint of this demand curve corresponds to a quantity of 15 and a price of 3. So we'll say example. Q equals 3, P equals 15. So we'll come back and plug those values in just a minute. But I'm just going to rewrite my elasticity formula here. Delta Q over Q divided by delta P over P. Now, this is maybe a little less ugly than the traditional midpoint formula, but I know how to take advantage, or I know how to make this a little bit neater. I'm going to take advantage of this rule when we're working with fractions that when one fraction is divided by another fraction, it's equivalent by multiplying by the reciprocal of the denominator. So let's come over here and do that. I can rewrite this formula as delta Q divided by 2 times the reciprocal of the denominator, P divided by delta P. And now I'm just going to rearrange those terms. Remember, when I'm multiplying, I can multiply in any order. Delta Q divided by delta P times P over Q. So now we have the elasticity formula in the point slope variation. Why do we call it that? Well, here, this expression corresponds to a specific point, a quantity-price combination. And this expression here corresponds to the slope. Now, we know that slope is rise over run, or change in y over change in x. So this is a little bit fast and loose with the slope. But notice, when I write my demand equation in this format, this is my slope coefficient, and it corresponds to the change in quantity, which is in the dependent variables place, divided by the change in price, which P is in the independent variables place. Okay, so I'm going to draw a box around this formula and go back over to this side so we can actually calculate the elasticity at the actual midpoint of this demand curve. And that will give us a really interesting result, which will be universally true. So I'm going to take my formula. Elasticity of demand is delta Q over delta P times P over Q using these values for P and for Q. And I know that delta Q over delta P for this demand curve is always going to be -5. I'm going to follow the convention that I used previously and drop the negative and take the absolute value, recognizing that if quantity is moving in one direction, price must be moving in the other direction. So delta Q over delta P is going to be equal to 5. My price in this, I have these backwards. Okay. My quantity is 15 and my price is 3. Here, I'll just make double check that, right? Q of 15, price of 3. So when I substitute my price, that's going to be 3. Q is going to be 15. I get 15 divided by 15, or a value of 1. Now you might recall that a value of 1 is what we call unit elastic. It corresponds to that situation where the percent change in quantity and the percent change in price are identical. They exactly match each other. Now that's sort of the boundary between being relatively inelastic or less sensitive to price and relatively elastic, where quantity is more sensitive to price. And this is always going to be true at the midpoint of a linear demand curve. Say the price elasticity of demand is unit elastic at that point. Now let's take a look at using this point slope formula to calculate the elasticity of demand at some points other than the midpoint. So I've chosen this point here at a price of 4 and a quantity of 10. I can use my same formula, and because I'm using a linear demand curve with a constant slope, delta Q over delta P is going to continue to be 5. Again, technically -5, but we're going to take the absolute value. So delta Q over delta P times P over Q. 5 times my value of price, 4, divided by quantity, 10. That gives me 20 over 10 equals 2. Because that value is greater than 1, that tells me demand in this range is relatively elastic. So we'll just say E equals 2. But in truth, any value, at any point in the demand curve above the midpoint, demand will be elastic. That tells me, again, if 1, that unit elastic value is kind of the boundary between elastic and inelastic, we should see below the midpoint of the demand curve gives us an elasticity value less than 1, telling us price elasticity of demand is inelastic. Let's confirm that by calculating the elasticity at the point where price is 2 and quantity is 20, or right here. So we'll follow the same formula. Delta Q over delta P times P over Q. Again, delta Q over delta P is going to be 5. My value of price is 2. My value of quantity is 20. That gives me a value of 10 over 20, 1/2 or 0.5. Because that's less than 1, demand is relatively inelastic. So we'll write in here that demand is 0.5. I'm going to try and draw a somewhat messy bracket and say that demand is relatively inelastic from the lower point, below the midpoint of the demand curve. Now, what's the intuition behind this? Remember, let's go back to our basic elasticity formula. How did we get started? Elasticity of demand equals percent change in quantity demanded divided by percent change in price. What's happening here? Up in these higher regions of the above the midpoint, or sort of the upper regions of the demand curve, we're starting with relatively small quantities. So a 1 or 2 unit change in price, or even a 5 unit change in price, is going to look relatively big. In fact, my slope coefficient tells me for every 1 unit change in price, quantity will respond by adjusting 5 units. Going from 5 to 10 is a doubling of quantity. That's like a 100% increase. That's driven by a drop in price from 5 to 4. That's about a 20% drop. So the percentage change in quantity looks relatively large compared to the percentage change in price. In terms of elasticity, that makes it seem like the quantity is quite sensitive to price changes. At the other end, the lower end of the demand curve, we have the opposite scenario. The change in price, even though it's the same unit change in price, looks relatively large in percentage terms. So as we go from 25 to 30, that's going to be an increase of about 20%. But that involves a price change or price drop from 1 to 0, which is sort of a 100% price drop. So my percent change in quantity looks relatively small compared to my percent change in price. And that fits in with the inelastic definition of elasticity, or less sensitive change in quantity given a change in price. So that's a naturally occurring phenomenon we'll see for any linear demand curve. Elasticity is going to be exactly 1 at the midpoint. It's going to be greater than 1, or elastic, above the midpoint or at higher prices. And it's going to be below 1, or inelastic, as price falls. Another way to think about this is consumers are in some ways most sensitive when they just start to be willing to buy a good or service. Once they're in the market altogether, we expect to see their sensitivity to price get lower. We're not going to see as large a percentage increase in quantity demanded for the same change in price as we saw at lower levels of consumption. Finally, we can calculate elasticity, or maybe not calculate the elasticity coefficient, but classify whether demand is price elastic or price inelastic by looking at revenue implications as we move from one price quantity combination to another. So I have my trusty demand curve down here. We'll just rewrite the equation. QD equals 30 minus 5P for completeness sake. What I want to walk through here is the difference in revenue from raising and lowering the price when demand is elastic versus when it's inelastic. And then we'll talk about the special case of being unit elastic. Now remember, if demand is relatively price elastic, it's saying that quantity is quite responsive to price. That means when price goes up, we'll say that quantity demanded goes down. Very scientifically here, a lot. And when price goes down, quantity demanded rises relatively a lot. Now, total revenue, which I'll just write here, total revenue is just price times quantity. Sometimes we might describe this as total consumer expenditure. Remember, as a consumer, I buy something, I'm spending money. As a seller, you're receiving that money, that is your income or your revenue. So these two things are equivalent. What happens here, when price rises and quantity demanded a lot, if I'm calculating revenue as P times Q, even though I'm earning a little more for each unit I sell, the number of units I sell falls so dramatically that my overall revenue will decline. So let's fill that in here. Total revenue falls. However, if I lower the price, even though I'm earning less per unit sold, I sell so many more units that my total revenue, P times Q, actually increases. So what we see when demand is relatively price elastic is that an increase in price drops the revenue, a decrease in price raises the revenue, or price changes move in the opposite direction as the revenue pattern. Now for inelastic demand, when quantity is less sensitive to price, we can probably predict what's going to happen. If demand is relatively inelastic, quantity doesn't respond very much. So when the price increases, quantity demanded will still fall, but only what I'll call a little. Likewise, if the price decreases, quantity demanded will rise, following the law of demand, but not by a very large amount, a little. So when we're calculating total revenue, we'll see that price-quantity combination here, when demand is relatively inelastic, I am selling fewer units, but not that many fewer, and I'm getting more money for each one I sell. We see that total revenue actually rises. Likewise, if I decrease price on a good for which demand is relatively inelastic, I'll sell more, but not very much more. So I'm selling a few more units, but I've taken a relatively large price cut on everything I do sell. That's going to decrease the total revenue. So what we see with inelastic demand is that the price movement or direction of the price change is the same as the direction of the total revenue. Now, unit elastic is a special case in between these two types of elasticities, And what we see with unit elastic demand is a change in price leads to no change in revenue. The change in revenue is, the price times quantity is exactly the same. Okay, so I want to take a look at maybe just calculating a couple numerical examples to confirm this. So let's take advantage of what we see on our demand curve here. So first what I want to do is look at a change in price from 5 to 4. That's going to correspond to quantity rising from 5 to 10. Now you might recall from our previous look at calculating elasticity, right at the midpoint, the value of the elasticity coefficient was 1. Above the midpoint, remember, so label my axes here, price changes are relatively small, quantity changes look relatively large in percentage terms, so elasticity is, the elasticity coefficient is greater than 1, or demand is relatively elastic here, and it's relatively inelastic here. So as we move from 5 to 4, what we'd expect to see is a result consistent with demand being elastic. As we lower the price, we would expect to see total revenue, or price times quantity, rising. So let's see what happens. Total revenue is P times Q, and it goes from 5 times 5 to 4 times 10 to 40. What did we see? Price falls, total revenue rises. That's consistent with demand being elastic or relatively sensitive to price. So I just want to put some numerical calculations here to confirm that. We could do that also by looking at, say, a change from 2 to 1. In that case, at a price of 2, my quantity demanded is 20. At a price of 1, my quantity demanded is 25. As I move from 2 to 1, I'm going from a revenue of 2 times 20 or 40 to a revenue of 1 times 25 or 25. In that case, I'm lowering the price, and I'm also lowering my overall revenue. That's consistent with inelastic demand. Okay, and as I said, right here, when the elasticity is 1, if we move sort of equally across that midpoint, say if the price changed from 2 to 4, what we would see there is, at a price of 2, the quantity demanded is 20. Total revenue is 4. If we leap over just to the other side of the midpoint, at a price of 4, quantity demanded is 10, total revenue is also 40. Even though we had a change in price and a subsequent change in quantity, the total revenue was unchanged. And that's consistent with the unit elastic portion of the demand curve. So to sum up, there's multiple ways to calculate elasticity. The most straightforward is when you have percentages and you can just substitute in the formula. But even if you're not given those percentages, there are alternate ways to figure it out. Sometimes we're looking for a specific elasticity coefficient, and sometimes we're just looking for a general sense of how sensitive quantity is to a change in one of its determinants.